a real-to-sim-to-real approach to robotic manipulation with VLM-generated iterative keypoint rewards. Consider this task where human asks to place the shoes on the rack. Because there is a box lying on the rack and there is not enough space for both the shoes, robot should not place the shoes directly. Rather, a better strategy would be to first push the box. Then place the first shoe, followed by the second shoe. This example shows that task specification is a critical capability in open-world environments where predefined rigid instructions can fail to capture the complexity of real-world interactions. Our task specification should be flexible, should align with human intentions, and should evolve iteratively. Towards this end, we propose to use VLM-generated reward functions as flexible task specification. By leveraging VLMs, we align robot behavior more closely with human intentions. These reward functions are generated iteratively until the task is finished. On the other hand, previous works that employ VLMs in robotics rely on fixed task specification, often unable to adapt to changes as the task progresses. We name our reward Iterative Keypoint Reward. Given an image and a human command, we automatically mark keypoints on the image. A VLM takes these as input and gives code which includes the overall plan and the current task. Then it predicts which keypoints we should interact with and where they should go. In this case, the VLM suggests to first push the shoebox to make space. Consequently, the code predicts that all the keypoints on the shoebox should go towards its left. Importantly, our keypoints are in 3D, not in 2D. It also predicts auxiliary information like whether we should grasp the object. These, along with keypoints, are used to generate a reward function. For the next step, the previous step's keypoint image and VLM output serves as execution history. Now the VLM takes current annotated image, along with execution history to predict for the next step. In our definition of keypoint reward, we have a scene. We reconstruct it in simulator. With iterative keypoint reward, we train a policy using RL. This policy is executed in the real world. We do this iteratively till the task is achieved. We show results for placing objects. On the left, the robot moves the shoe from the table to the rack. On the right, it stows the book on the shelf. We also present results for pushing objects. On the left, the robot pushes the shoe to form a matching pair. On the right, it pushes the book, aligning it to other one. Unlike previous works, our RL training accounts for dynamics and can achieve non-prehensile manipulation. This example demonstrates the robot's multi-step chaining ability for a human command that would require 4 sequential actions, first placing the pair of pink shoes and then the black shoes. In this scenario, a human interrupts the robot while it is halfway in placing the shoes on the rack. The system's robust framework effectively handles the disturbance. After the robot places the right shoe, a human moves it back to the table. Despite this change, the robot successfully adapts by continuing to place the right shoe on the right side, even though it is now positioned on the left. Subsequently, the robot proceeds to place the left shoe as intended. In this case, we show an example where the framework corrects itself. The task is to place the shoes on the rack. The robot first places the right shoe as intended. When the robot attempts to place the left shoe, it realizes that the shoe is not positioned close enough to the right shoe. To address this, the VLM predicts a corrective action, suggesting that the robot push the left shoe closer to form a proper pair. In this case, the robot is tasked with stowing a book on a shelf. However, the initial grasp attempt fails because the book is too large to be grasped. In response, the VLM predicts an alternative strategy to complete the task. The robot first pushes the book to the edge of the table to facilitate a successful grasp. After that, it stows it on the shelf. For more details, please refer to our paper. Thank you.